measures of variation. We are going to look at measures of variation. It was part of the objectives that was discussed for the whole topic of describing, exploring, and comparing data. In this topic, measures of variation, we are going to consider the following: range, standard deviation, and variance. Range is defined as max minus mean. And again, just like a mid-range, and you don't want to mix them up, mid-range is the sum of the two divided by 2. It is obviously not resistant to outliers. It is affected by outliers. It can't get any worse than that. Remember that, max minus mean. Then we look at the variance, standard deviation, coefficient of variance. Sometimes they call it CV, sometimes they call it CVAR, which is simply the ratio of the standard deviation to the mean. If you're looking at sample, we use S over X. If you're looking at population, we use sigma over mu. And that 100% is changing it to a percentage. Chebyshev's theorem, it refers to distributions that are not normal or in general, and it uses the formula 1 minus 1 over k squared. K is the number of standard deviations away from the mean. Empirical rule, or the normal distribution, is referring to the picture on the right side. If you start with the mean and you go one standard deviation away, it covers 68% of the data. If you start from the mean and you go 2 standard deviations away, it covers 95%. And if you go 3 standard deviations away, it covers almost everything, 99.7%. We also have range rule of thumb for understanding standard deviation, which divides the range divided by 4. And the reason it does, because normally 95% is good enough for everybody. And remember, 95% means 2 standard deviations away from the mean. So that means mu plus minus 2 sigma, or S plus minus 4 plus minus 2S. That would be for example. All right, range.
The range uses only the maximum and the minimum data values, so it is very sensitive to extreme values. Therefore, the range is not resistant. It does not take every value into account and does not truly reflect the variation among all of the data values.
We have 2 brands of paint, and we are testing to see how long each will last before fading. So the result is given in months. We have a sample of 6 cans. We want to find the mean and the range for each group, and then which brand will be used. So it's a simple process. If you look at brand A, you are finding the mean. X bar is summation of X over N. It's a simple process. You add them up and divide by 6. And the same thing for brand B. To find the mean, add them up, divide by 6. As far as the range is concerned, for brand A, you really have to rank it, but largest number is 60 and the smallest number 10. So 60 minus 10, that is what we are going to use to calculate the range, 50. And by the way, the units are the same. 35 months is the mean, 50 months is the range. We do the same thing for brand B, and we notice that the largest number is 45 and the smallest number is at the bottom is 25. So that would be the difference between the two as far as the range is concerned. So clearly, we notice they have the same mean. The average number of months that they're going to last is the same, but they have different range. The range is different for both. So which one would you buy? What do you think, class?
Brand A.
Well, brand B, I would pick brand B because you know what you would get. You might have a 10-year one with brand A or a 6-year one, but you don't know.
Absolutely. It is more consistent. It's all about consistency. Brand B is more consistent. According to this calculation, brand B is more consistent. The next topic is the idea of a variance.
The variance is the average of the squares of the distance each value is from the mean. The standard deviation is the square root of the variance. The standard deviation is a measure of how spread out your data are and how much data values deviate away from the mean.
But that's how variance works. And what we are interested in is normally standard deviation, not the variance, but we need the variance to get to the standard deviation. So with that being the case, as far as the notation, S represents the standard deviation for a sample. Sigma represents the notation for population standard deviation. Usage and property.
To determine the spread of the data, to determine the consistency of a variable, to determine the number of data values that fall within a specified interval in a distribution, used in inferential statistics, the value of the standard deviation S is never negative. It is 0 only when all of the data values are exactly the same. Larger values of S indicate greater amounts of variation.
This is important to understand. When it comes to standard deviation is never negative, because if you look at the formula, you see that the top is positive, so is the bottom, and you take a square root. And the only time it becomes 0 when all data values are exactly the same. And remember, when you are producing something, product, a company, a factory is producing something, we like to have less variation. So it is optimal to have 0 standard deviation. That means product 1 and product 2 are identical. They're going to last the same in essence. That's the idea behind that. Obviously, standard deviation is affected by outliers. The units are the same, and the sample standard deviation is considered a biased estimator of the population standard deviation sigma, which means that values of a sample standard deviation do not center around the value of sigma. We'll discuss this concept of an estimator in later chapters, but here's the formulas. Let's see how it's calculated. Obviously, you can use a calculator to do the calculation, but for small data, we should be able to do it by hand, just for practice. As far as the variance is concerned, the summation of x minus mu quantity squared over n. By the way, again, x or lowercase or uppercase mean the same thing. Normally, we use the lowercase. The thing that is important is for population, understand you're using the Greek letters sigma and mu, and this is capital N. Lowercase n is used for a sample size. If you are interested in finding the standard deviation, all you have to do, take a square root of the top formula. So normally the top formula is calculated, then you take a root and it becomes a standard deviation. This is the reason it's important to distinguish between a sample and a population variance. We divide by n minus 1 instead of n when it comes to a sample variance. And in order for you to calculate the standard deviation, all you have to do, take a root. But there are 2 ways to calculate the sample variance. This is just the same concept as this one. It can be extended and it can be proved that this will do the job also. Sometimes it may be easier to use that one. Again, I will show you with a simple example in a moment, but generally speaking, you use technology to come up with the answer. It's important, however, to understand the methodology. By the way, for the variance, as far as the units are concerned, it's the same units as the data, but squared. But when you do the standard deviation, then you have the same units. Now, again, you calculate the variance, you take a root, and it becomes a standard deviation in both cases. So you calculate the sample variance or the population variance. You take a root, becomes a standard. In other words, you really don't have to do calculation 2 times. One is simply the root of the other one. Or if you're given the standard deviation, you can square it and get the variance. As you remember, we do have the formulas and tables and usage of a calculator. So I put the information here also that's handy for a TI calculator. You can enter the data as follows. Click on Stat, Edit, and you want to clear, and then type in the data in, for example, L1. Then you can check by going to 1, again, Stat, Calculate, select 1 for one variable, and type is L1. when you want to type it. And to do that, you do second one to type that. And you can see the summary if you scroll down. I highly recommend you guys try it on your own when you have a piece of data and you want to calculate something. See if you can use your calculator that way. You can try it, and it's fairly nice and easy. So here's a very simple example we want to look at here. We are repeating the same question, but we are finding other things in this case. We want to find the range. We have to rank the data, or in this case, maybe it's small enough even without ranking, you can see it, but it's a good practice to rank it. In order for you to find the range, you need the largest minus the smallest. The max minus mean, 55.6 is the largest, and 14.1 is the smallest. Put it in descending order or ascending order. In this case, ascending. Rank it from smallest to largest to be on the safe side. To calculate the standard deviation, take a look at the formula. We need to find x bar. Therefore, let's find x bar. What is x bar? Add them up, divide by size. And we have the answer. Now, what about standard deviation? You can just find the variance and then take a root, or you can put it under the radical in one shot. It really is up to you. It doesn't make any difference. We are interested in calculating S. Why is this S? And that's important for everybody to realize. You're looking at a small piece of data. It's only 5 pieces of data. If you look at the formula, summation of x minus x bar, that means every piece in your data. Look at the data. The very first one is 38.5. So 38.5 minus 30.7 has to be squared. And this is why the standard deviation or variance for that matter, it's non-negative. Can it be 0? Yes. All values are the same, it can be 0. But can it be negative? Absolutely not. Why not? Because the numerator is positive. Why is it positive? Because it's the sum of the square of numbers. The denominator is positive. Why is that? Because it's the sample size minus 1, which is still a positive. So with that being the case, all you have to do, 38.5 minus 30.74 squared plus 55.6 minus 30.74 squared, and all the way to the end, and divide by n minus 1, 5 minus 1. If you take a root, we have the standard deviation. Calculation in this manner is not a big deal. I will show you a different calculation too, because I want you to be exposed to it. You should know how it's calculated by hand. But if we have too many, the data size is large, we can use the technology. Now, here's what I mean by many decimals. It is important to keep the numerator with many decimals. You divide by 4, you take a root, and eventually you do the rounding. So you don't want to do the rounding too early. If you put the numerator the 4 decimals with only 2 decimals, then your result here may be wrong. So your standard deviation is 16.45. If somebody's asking, what is the variance? It's the same thing, square it. 16.45 squared. Normally, we are not interested in variance. In many cases, in order to get to it, it's easier to just not to write the root, calculate the variance, and then take it. So this is the method that we are simply subtracting the mean from each piece of data. We square them, we add them up, and divide by n minus 1. We're taking the average of the differences. So with that being the case, here's the second method I want you to see quickly. If you recall and you go back to the formulas, another way of calculating this was the square root of n summation of x squared minus summation of x quantity squared over n times n minus 1. I want to make sure everybody understands the meaning of summation of x squared and summation of x quantity squared. We don't want to mix them up. So I'm going to write down the summation of x squared. Summation of x squared means 38.5 squared plus 55.6 squared all the way to the last one. That is the summation of x squared. However, summation of x squared means add them up, 38.5, 55.6, all the way to the last entry, and now square that. So I'm mentioning that because I want to make sure we know how we calculate each one and we don't want to mix them up. Summation of x squared versus summation of x quantity squared. Again, two different methods of calculation. You choose the one that works for you. I expect you to be able to do it on your own for small sample data. We're going to get another example. You want to find the variance and standard deviation, and it's telling us we are dealing with the population. Let's assume it's the population. Therefore, we are going to use the sigma and mu. So first thing first, you need to calculate the mu. Add them up, divide by size, and we get 35. In order to find sigma squared, you want summation of x minus mu quantity squared divided by n. Summation of x minus mu quantity squared. So let's calculate x minus mu. So the first one would be 10 minus 35. The next one would be 60 minus 35. And the next one would be 50 minus 35. And here's the column, which is the third column. Now, the fourth column will square the third column. So negative 25 square it, 625. And do the same thing with the rest of them. And we need to add them up. So this is x minus mu squared for each case. Now the summation would be to add up this one. And what you are looking at, this one, is the following summation. Summation of x minus mu quantity squared. In other words, this is the numerator of the variance. For mu class, please change it to 6. That is the variance. Standard deviation, you just take a root. So you take a root, and that would be the standard deviation.
Find the variance and standard deviation for the amount of European auto sales for a sample of 6 years. The data are in millions of dollars.
It's important to pay attention that this is a sample. The variance S squared is summation of x minus x bar quantity squared over n minus 1, or n summation of x squared minus summation of x quantity squared over n times n minus 1. There are two different ways of calculation. Let's look at this method of calculation. Again, for practice, we are looking at various types. Needless to say, as you've seen, in all cases, we are using a small size data because we want it to be manageable when we do it by hand. And so if you look at the formula, the numerator needs the summation of x squared and then summation of x quantity squared. So first, let's square the first column. So we get 11.2 squared, 125.44, and you move on with the rest. Now, when you add up, this one is summation of x when you add up the first column. Now, when you add up the second column, this one is summation of x squared. And so we put that into the formula. And remember, n is 6, by the way. N, which is 6 times 958.94 minus 75.6 quantity squared divided by n times n minus 1, 6 times 5. And it gives us s squared. To calculate s, all we have to do, take a root. So the standard deviation is 1.13 in millions of dollars. $1.13 million. We looked at calculation of standard deviation and variance for a few cases, small sample size on purpose. Range rule of thumb.
The range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. The vast majority, such as 95% of sample values, lie within 2 standard deviations of the mean.
So that's why it's used as a standard, if you will, mu plus minus 2 sigma, or for a sample would be x bar plus minus 2s. If it's beyond those two, or if it's less than mu minus 2 sigma, or if it's greater than mu plus 2 sigma, those are considered unusual. So if it's unusually high or low.
To roughly estimate the standard deviation from a collection of known sample data when the distribution is unimodal and approximately symmetric, use S is approximately range over 4.
This distance from here, if you will, to here is 4 sigma. And if that is the case, and you normally don't have access to the population, normally we don't have access to the population standard deviation, we can, if we have that range, we can divide it by 4, and that would be the standard deviation we are going to use. And so range rule of thumb, mu plus minus 2 sigma, range rule of thumb. Within that, and if it's other than that, beyond that, it's unusual. Usual within mu plus minus 2 sigma. This graph was given in the beginning when we discussed the synopsis of what we did. This is known as the empirical rule.
The empirical rule states that for data sets having a distribution that is approximately bell-shaped, the following properties apply. About 68% of all values fall within one standard deviation of the mean. About 95% of all values fall within 2 standard deviations of the mean. About 99.7% of all values fall within 3 standard deviations of the mean.
And those are the numbers we come across often, especially when we go to normal distribution and deal with later chapters. We should be familiar with these numbers. Empirical rule applies to a bell-shaped, a symmetric, and normal distribution. Otherwise, it doesn't apply. And that's why the Chebyshev's theorem was discussed, and we're going to look at that also. Now, according to the empirical rule, when you start from the mean and you go one standard deviation away on each side, that's 1s, if you will, or 1 sigma if it's mu. That covers about 68% of the data. 2 standard deviations, 95%, 3 almost all, 99.7%. And why is this important? If you're producing something, if your target is such that you want to target 95% of the population, then you are not going to go beyond 2 standard deviation because the cost may not make it worth it. If you want to go more than that, if you want to target more than that, if you go within 3 standard deviations, you cover almost everyone, 99.7%. So that is really an important piece of information, and you're supposed to know those values. IQ scores have a bell shape. So it is mentioned that you are dealing with an empirical rule. With a mu of 100, mean is 100. So that's mu. And sigma is 15. Mu is 100. Sigma is 15. What percentage of IQ scores are between 70 and 130? Now, this is really referring to the previous page. All you have to figure out is how many standard deviations away from the mean are the two numbers. Now, I want to show you an easy way of approaching this, and then we look at the calculation also. So if you are dealing with this, the concept is very simple. You have the mean. We're going to go to the left, and we're going to go to the right. To the left is number 70. To the right is 130. Now, as you all see, the difference in both sides is 30 units. It's clear. 130 minus 100 is 30, 100 minus 70 is 30. So on each side, we go 30 units. Now, 30 units really doesn't mean anything. What matters is that what does it translate into, meaning how many standard deviations. So the distance of 30 is not good enough. We want to know it corresponds to how many standard deviations. And because the standard deviation is 15, 2 times 15 is 30, so it corresponds to 2 standard deviations. It corresponds to 2 standard deviations away from the mean on both sides. And therefore, now you have the answer, which is 95%, according to empirical rule. We want to approximate the lowest value and the highest value in a data set where X bar is given as 10 and R is given as 12. Remember, we want to go with mu plus minus 2 sigma or X bar plus minus 2s. That's the idea. And so s, if you go back to the range rule of thumb, we said because we say plus minus 2 sigma is the total of 4 standard deviations, or the range is given, if we divide it by 4, it gives us an approximation for s. And so x bar plus minus 2s gives us the answer. 10 plus minus 2 times S3. So 10 minus 6, 10 plus 6, and that gives us the low of 4, high of 16. So this is empirical rule, range rule of thumb, which refers to starting from the mean, you go 1 standard deviation, or 2 standard deviations, or 3 standard deviations, what happens? That's the idea. The 2 standard deviation is considered a range rule of thumb and good enough for most everything.
Professor, I just have a quick question.
Sure.
I'm just trying to keep track of all the variables and all the symbols. What is the X with the line over it symbol?
X bar represents the sample mean.
Sample mean. Okay, gotcha.
X bar sample mean, mu is population mean. Chebyshev's theorem, the proportion of values from any data set that fall within k standard deviations of the mean will be at least 1 minus 1 over k squared, where k is a number greater than 1, and it may not necessarily be an integer. In the table, I'm showing you the calculation for a couple of them. For example, if k equals 2, 1 minus 1 over 2 squared is 1 minus 1/4 is 3/4, and it corresponds to 75%. So I'm just discussing this one. 2 standard deviations mean k is 2, square root is 4, 1 over 4, subtract that number from 1 is 3/4, is 75%. 3 standard deviations away, 3 squared becomes 9, 1 over 9 subtracted from 9 is 8 over 9, precisely about 88.89%, so on and so forth. When do you use that? When the data is given and we don't know anything about it.
The mean price of houses in a certain neighborhood is $50,000 and the standard deviation is $10,000. Find the price range for which at least 75% of the houses will sell.
If we look at the table, we really don't have to do much. 75% corresponds to 2 standard deviations as far as the Chebyshev's theorem is concerned, and at least 75% happen within 2 standard deviations of the mean. So we are going to do the calculation. Are we using X bar or mu? Which one is which? Is it a sample? Which one is that and why?
Isn't it mu because we're just looking at the houses in that specific neighborhood?
Exactly. It refers to all. Here's how you know it's a population. Population refers to all somehow. This doesn't say the mean price of houses, 10 houses in the neighborhood, or 20 houses, or even 200 houses. It says the mean price of houses in a certain neighborhood. That means all. That means mu is 50 and sigma is 10k. And you're looking at mu plus minus 2 sigma. It is extremely important to know it is referring to population. What we need to know now, why Chebyshev's theorem?
Oh, I was just gonna say that it's because it's asking how many, like, find the price range of for at least 75% of the houses will sell. So therefore, we want to know like a certain percentage of the range that we have. So therefore, we need to be able to find like the values that will be within that 75%. So then that's why we use Chebyshev's theorem.
But why Chebyshev's? Why not empirical? We use Chebyshev's theorem when we don't know anything about the distribution. The distribution is not mentioned to be normal. By that, therefore, we have to use Chebyshev's theorem. That's important to see. Chebyshev's theorem because we don't know about anything about the distribution of the prices.
A survey of local companies found that the mean amount of travel allowance for executives was 25 cents per mile. The standard deviation was 0.02. Using Theorem, find the minimum percentage of the data values that will fall between 20 cents and 30.
We know it's 1 minus 1 over k squared. So the standard deviation is given, 0.02, and the mean is given. So we need to know how far we are from the mean. And again, it is asking for Chebyshev's theorem. But if it wasn't, we should know it's using Chebyshev's theorem because it doesn't say anything about the distribution being normal. So with that being the case, you need to know how far you go to get to that number. So look at this one this way. To the left of it is 0. To the right of it is 0.3. And the distance between those two numbers and 0.25, which is the same, by the way, it should be the same for you to come up with the answer, has to be divided by sigma to give us k, the number of standard deviations. So 0.3 minus 0.25 or 0.25 minus 0.2, they give us the same answer. In both cases, the answer is 0.05. You divide by the standard deviation sigma to get to k, and that's 2.5. Now, according to Chebyshev's theorem, we say 1 minus 1 over k squared. So 1 minus 1 over 2.5 squared. Now you need to calculate this and subtract it from 1. And that works out to be about 84%. Comparing variation in different samples or population, we use what's called coefficient of variance. They call it CV or CVR or COVR, depending on the text. It is the ratio of the standard deviation to the mean, and then you can change it to a percentage. So coefficient of variance is defined for a set of non-negative sample or population expressed as a percent, describes the standard deviation relative to the mean and is given by the following. The standard deviation divided by the mean expressed as a percentage. And as I mentioned, CVAR or CV, sometimes COV. The short notation CV is good enough. When the units are different, normally that's a good thing to check. So let's look at the example of that. The mean of the number of sales of cars over a 3-month period is given as 87. This is mu, all cars over the course of 3 months. And the standard deviation sigma is 5. So that's for the cars. For commission, the mean is 5,225 and the standard deviation is $773. We want to compare the variation of the two. There are two different things completely. So we want to compare coefficient of variance. So with that being the case, the first one, this would be mu, this would be sigma. For cars, this would be mu, this would be sigma for commissions. So we divide the standard deviation by the mean, and then we change it to a percentage. So car sales, the number of cars, if you will, okay, the percentage, you can say car sales. And for commission, 773 divided by 5225. And again, it's changing to, it is extremely important that you write it as, if you wrote it as 14.8 or 5.7 is wrong. You can, even if you left it as a fraction, I'm okay with that, but understand they want it in percentage. If you left it as 14.8, it is wrong. And so that's extremely important to understand. So with that being the case, when you compare, the second one is larger and second one has more variation. So commissions are more variable than sales of cars. All right, the next topic is measures of relative standing and box plots. We discussed measures of center, such as mean, mode, mid-range, weighted mean. Measures of variation, such as range, variance, standard deviation, coefficient of variance. We also looked at the empirical rule, the range rule of thumb, and Chebyshev's theorem. We also looked at their formulas and different notations, and it's extremely important to see that when you are dealing with a question, you have to realize whether you're dealing with a sample or a population. So you want to make sure you use the proper notation. Measures of relative standing and box plots. The key concept in this section gives us measures of relative standings, which are numbers showing the location of data relative to others within the same data. So here's the synopsis of what's coming up. The z-score, when you ask your instructor, are you going to curve the grade, you're referring to z-score is defined as x minus x bar over s or x minus mu over sigma. Percentile, it's calculated as the number of values below a specific number divided by total number of values. That 100% just changes it to a percentage. Percentile locator, notice we use L. In some cases, I've seen that they use C. N is dipole size, but notice K over 100 or P over 100. A percentile, in many texts, they use P. In some cases, they use K. So again, I want to make sure that you're familiar with various notations. Quartiles separates the data into 4 equal groups, Q1 or P25. Q2 is the same as the median, and Q3 is P75. Outlier. How do we find an outlier? I've mentioned the concept of outlier before, which means something is way off, but now precisely a value which is less than Q1 minus 1.5 IQR or Q3 plus 1.5 IQR. We see what that means shortly when we look at box plots and 5-number summary, which requires 5 numbers minimum, those 3 values, and the max. What is a z-score? A z-score or standard score is the number of standard deviations that a given value is above or below the mean. It is obtained by subtracting the mean from the value and dividing by the standard deviation. So pay attention to the formula z equals x minus x bar over s, or z equals x minus mu over sigma. The important properties of the z-scores.
The z-score is the number of standard deviations that a given value x is above or below the mean. Z-scores are expressed as numbers with no units of measurement. A data value is significantly low if its z-score is less than or equal to -2, or the value is significantly high if its z-score is greater than or equal to +2. If an individual data value is less than the mean, its corresponding z-score is a negative number.
If your z-score is 0, that means your score is the same as the average in class. If your z-score is positive, that means above the average in class. If it's negative, it means below the x-axis. Okay, that's the bottom line. And that 2 and -2 that you see, remember mu plus minus 2 sigma to the right, 2 sigma to the left. Those are the concept that we've seen. Okay, so the same thing that was discussed previously as far as the empirical rule and the range rule of thumb is concerned. Let's see what we mean by that. Let's start with a very simple example.
Which of the following 2 data values is more extreme relative to the data set from which it came? The 400-gram weight of a baby, n equals 400, x bar is equal to 3,152.0 grams, s equal to 693.4 grams. The 99-degree Fahrenheit temperature of an adult, n is equal to 106, x bar is equal to 98.20 degrees Fahrenheit, and s is equal to 0.62 degrees Fahrenheit.
It's very simple. We have to put that into the formula, okay? And the top right formulas in blue give us the z-score and how we calculate it. They are very similar, x minus x bar over s or x minus mu over sigma. We are dealing with a sample. We use the first one. If by any chance you're saying you're using the second one, the numbers work out the same, and in this case, it doesn't make that much of a difference. But it does make a difference in other cases, so you want to be careful using the proper formulas. So for the babies, so you're going to put x minus x bar over. So you put in simply the numbers, and you end up with 4,000 grams minus 3152 divided by S, which is 693.4. Now, notice N is 400, but doesn't come to play. N is just a piece of information. It's important to know the sample size. It doesn't come to play here. And you have the answer. The second one, the x value is 99 minus x bar, 98.2, divided by s, which is 0.62, 98.2, and you calculate it. And obviously, the second one is larger, has a larger z-score, which is the temperature. Sounds good. Just make sure that number is changed to 98.2. Here's the next one.
A student scored 65 on a calculus test that had a mean of 50 and a standard deviation of 10. She scored 30 on a history test with a mean of 25 and a standard deviation of 5. Compare her relative positions on the two tests.
You have to calculate the z-score. What is the score? If you look at the first one is 65, that's the score, x. The mean and the standard deviation, that's the first one, you calculate it. The next one is 30, so this is the x amount, if you will, the score. The mean is 25, so mu is 25, standard deviation. And you calculate that, and you end up with 1. Therefore, which one is higher? Clearly, according to the z-score, the first one. Let's look at one more similar example for the z-score.
The lowest platelet count in a data set is 75. Platelet counts are measured in 1,000 cells per microliter. Is this significantly low? X bar equals 239.4, S equals 64.2.
Okay, so we just used the z-score to figure out what's going on. According to the z-score, x minus x bar over s. This is the value we use for x. So we do this simple calculation, and it gives us negative 2.56. Now, first of all, it's on the negative side, and that's why they are asking if it's significantly low. Let's assume instead of 75, we had a larger number and it ends up being positive. They would ask, is it significantly high if it's positive, okay? Now, if you recall, the range rule of thumb says mu plus minus 2 sigma is fine and beyond is unusual. If this number is larger than 2 or smaller than negative 2 is unusual. That's basically it. So you have your answer there. Z is less than negative 2 and therefore is significantly low. Why we are saying it's significantly low or significantly high? We are comparing it to two numbers. One of them is negative 2, one of them is positive 2. So less than negative 2 and larger than, or if you will, I should say, larger than 2, it's considered unusual.
Percentiles are measures of location denoted P1, P2, P, etc., P99, which divide a set of data into 100 groups with about 1% of the values in each group. Percentiles separate the data set into 100 equal groups. A percentile rank for a datum represents the percentage of data values below the datum. Round the result to the nearest whole number.
Here's how the percentile works. Number of values below x divided by the total number of values. Now that 100% just changes it to percentage. I want you to see the concept. What's important is to see this one. In some texts, they use that and they add 0.5. Why am I giving you that formula? And that's not the formula that we use it in this text. In some texts they do, and I want to mention that some of this stuff in stats calculated slightly different. If you use different technologies, sometimes you come up with different answers, but they differ by a little bit, just to let you know. However, for a large N, for a large size of data, they're almost identical. N is the total number of values or the sample size or even the population size. K is the percentile, like P sub K, if you will. L is the locator. Where is it located? For example, for 12th value in the sorted list, remember it has to be sorted. L is 12, and PK or Kth percentile example, P25 is the 25th percentile. Now look at the formula. We can say K over 100 times N or P over 100 times. And remember that K over 100 is that really the percent format of the K. So when we say 25th percentile, just as an example, 25th percentile, that means 25 over 100. So if you're looking at 25th percentile, that means what? 25 over 100. That's the meaning of K over 100. Notice in the next formula, I say P over 100. Depends on the text. But understand, if you come across a different format, you don't want to be thrown off. So with that being the case, let's start with this simple example. We have 50 cell phone data speeds as follows and are arranged in increasing order. I want to make sure everybody pays attention to this, because if it's not, you have to do that. So this must be arranged. Because this contains 50 pieces, that's a lot, and we don't want to waste time. It may not be given to you in this format. You have to arrange it, but this is given in arranged format. It is ranked, and therefore it makes life easy. So that's the first thing I want everybody to notice. And so for number 11.8, we want to find the percentile for 11.8. And the top gives us the formulas that were given. Percentile refers to the number of values below a specific number. Look at the top, says below X. What is X in this case is 11.8, everybody. Divided by the total number of values. So where is that number? It's 11.8 here. So the rest of it, the first row and the second row are smaller than 11.8. And in each row, we put 10 numbers, class, to make life easier. 10 numbers in each row. So we have a total number of what? 10 plus 10, 20 numbers that are smaller. So really, I want you to see this number. This is what I'm interested in. This is really your answer. Now the rest is changing it to a percentage. In other words, your answer is 2/5. So the number of values below 11.8 divided by n, total size, that's really your answer. So the answer is 2/5. Because it says percentile, we change it to a percent. That's all. That's why that 100%. So with that being the case, here's the interpretation. A data speed of 11.8 megabit per second is in the 40th percentile and separates the lowest 40% of values from the highest, now 100 minus 40, 60% of values. So we have P40, P sub 40 equals 11.8. All right, we're going to go to the next one. We want to find the 20th percentile and then 87. So we are looking at the same piece of data. So we're going to look at part A. We are repeating the same question essentially. You can think of continuation of the same question. So look at the formula at top. L equals K over 100 times N, or P over 100 times N. We want to locate that. So here's the procedure. You want to rank the data. It is ranked already. We want to find index or locator. So they call it locator or they call it index. L, which is K over 100 times N. K is the percentage, or P, K or P, whatever you want to call it. And N is the sample size. So I don't want to get hooked up with those variables because depending on the text, they use different variables. And so L is not a whole number, rounded up. If it's 2.1 or 2.9, makes no difference. You go to the next number, which is number 3, the third one. So it's not a whole number. 14.1 or 14.5 or 14.7. You go up to the next one. That's the idea. If it's a whole number, the K percentile is the average of that value and the next one in your data. So this is the methodology. Again, this is something that statisticians have come up with. They don't agree on that 100%. That's why sometimes you see that 0.5 being added. So having said that, K is 20, N is 50. So you really have 0.2. 20th percentile is 0.2, if you will. 20th percentile Okay, remember, p20, we are looking at p20. P20 is what? 0.2, 28th percentile. 20 over 100, or 0.2, or 20%. So I want to make sure that everybody understands this part comes from the fact when we say p20, it means what? We are dealing with 20%. That's how we get 20. So it's really not that big of a deal. Again, times 50, and it gives us a whole number. Because it is a whole number, you locate that, you use the next one, you take the average of the two. So this is the 10th one, 6.2. And the next one is 6.5, add them up, divide by 2. I want to make sure everybody understands what's happening here. We are dealing with a whole number. Look at the procedure, step number 4. Because it's a whole number, use the next one as well. Part B, 87th percentile, or 0.87 times n, 0.87, however you want to put that. And so you end up with 43.5. Again, I'm going to emphasize, class, 43.5 or 43.1 makes no difference. You go up to the next one, 44th piece. You need the 44th piece. So you got to count, and here's the 44th piece when you do the counting, or you can go down, it's easier, go down from 50. And the answer is 28.5, and you use the proper units as given.